Welcome to C005 Electrochemistry and Redox Reactions.
Every smartphone battery, every electroplating process, every nerve signal in your body involves the controlled transfer of electrons.
Electrochemistry is the branch of chemistry that studies the relationship between electrical energy and chemical reactions.
Today we will master oxidation states, redox equations, galvanic cells, and Faraday's laws. This is a topic that rewards careful systematic thinking, and it comes up reliably in NEET every single year.
Here is a demonstration you can do at home. Press a zinc nail and a copper coin into a lemon. Connect a small LED between them. It glows. The lemon is acting as a battery. Zinc on the left is oxidizing, losing electrons, acting as the anode. Those electrons flow through the wire to the copper, which acts as the cathode where hydrogen ions from the lemon juice accept the electrons. The lemon juice is the electrolyte, completing the circuit.
The voltage is only about 1 volt, not enough to charge your phone, but enough to prove the principle. Every battery you own, from AA cells to lithium-ion packs, uses this exact same galvanic cell principle, scaled up and optimized with better materials.
Redox reactions involve the transfer of electrons between species.
Oxidation means loss of electrons, the oxidation state increases.
Reduction means gain of electrons, oxidation state decreases.
They always occur together. You cannot have oxidation without reduction happening simultaneously somewhere.
The mnemonic oil rig is worth burning into your memory. Oxidation is loss, reduction is gain. The oxidizing agent is the species that gets reduced, it takes electrons from something else. The reducing agent is the species that gets oxidized, it donates its electrons.
For assigning oxidation states, oxygen is almost always -2, hydrogen almost always +1, and all neutral atoms in their elemental form have oxidation state 0.
Two types of electrochemical cells are tested in NEET. A galvanic cell converts chemical energy to electrical energy spontaneously.
The cell potential E degree cell equals E degree cathode minus E degree anode using standard reduction potentials from the electrochemical series.
If this is positive, the reaction is spontaneous.
The Daniell cell zinc and copper electrodes is the classic example. Zinc is the anode with E degree -0.76 volts, copper is the cathode with E degree +0.34 volts, giving a cell potential of 1.1 volts.
An electrolytic cell is the reverse. You supply electrical energy to drive a non-spontaneous reaction.
Electroplating, anodizing, and industrial production of aluminium from molten alumina all use electrolytic cells.
Remember, in both types of cell, oxidation always happens at the anode and reduction always happens at the cathode. Faraday's laws are the quantitative foundation of electrolysis.
The first law states that the mass of substance deposited at an electrode is directly proportional to the total electric charge that passes through the electrolyte. The formula M equals mQ divided by NF combines molar mass M, charge Q in coulombs, number of electrons transferred N, and Faraday's constant F, which is 96,500 coulombs per mole. In our worked example, 2 amperes for 30 minutes deposits copper from copper sulfate solution. We calculate charge as current times time equals 3,600 coulombs. Then substituting into the formula with N equals 2 for copper 2+, we get 1.19 grams of copper deposited. This calculation type appears frequently in NEET as a direct numerical problem. The key relationships in electrochemistry all connect to each other beautifully.
Cell potential equals E degree cathode minus E degree anode. A positive cell potential means a spontaneous reaction. Delta G equals -N times F times E degree links electrochemistry to thermodynamics.
When cell potential is positive, delta G is negative, confirming spontaneity.
The Nernst equation adjusts the cell potential for non-standard concentrations.
At 25 degrees Celsius, the simplified form uses 0.0592 over N times the log of the reaction quotient. As the reaction proceeds and concentrations change, the cell potential decreases until the cell is fully discharged, when Q equals K and E equals 0. Faraday's constant is 96,500 coulombs per mole, the charge carried by 1 mole of electrons.
For NEET electrochemistry strategy, cell potential and Faraday's law calculations are the most frequently awarded marks. Practice the Faraday's law calculation until it is automatic. Write the half reaction to find N, calculate Q as I times T, then substitute. For cell potential, always use standard reduction potentials, always put cathode minus anode, never add potentials. The electrochemical series lists species in order of reduction potential. A species higher in the series is a stronger oxidizing agent and will oxidize any species below it. The mnemonic in OX red cat anode oxidation, cathode reduction works for both galvanic and electrolytic cells. Students sometimes reverse these in electrolytic cells, do not. Oxidation is always at the anode. The 5 takeaways from C005. 1. Oil rig oxidation is loss, reduction is gain, never forget this. 2. Galvanic cells are spontaneous with positive E-degree cell, anode undergoes oxidation, cathode undergoes reduction. 3. Cell potential is cathode minus anode using reduction potentials, always subtract. 4. The Nernst equation corrects for real conditions where concentrations differ from standard. 5. Faraday's law mass deposited equals mQ over NF is your tool for all electrolysis calculations. In C006 we move to chemical kinetics, how fast do reactions go, and what controls the rate? A topic deeply connected to everything we have studied so far. See you there.